Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Our today lecture includes the topics thermal expansion of solid, the thermal expansion of solid, the linear thermal expansion, and the volumetric thermal expansion. Class, you know that when you are in the junior classes, then you might have come across with one sentence that substances expands on heating and contract on cooling. So today we will apply this effect to the solids and liquids, and we will study it in great detail, particularly its application or merits and demerits in our daily life. So let us start with our topic. The first topic is the thermal expansion, the linear thermal, the linear thermal expansion, the linear thermal expansion of solids. So what is the linear thermal expansion? It is the increase in the length of an object or the size of an object due to heating, or best is due to rise in its temperature, So this is known as the linear thermal expansion. Now we will explain the concept of the linear thermal expansion. For this purpose, we will consider as that is the a metallic rod which original length is L. As you see, this is the area of cross section of the metal rod. Okay, so you see that that it has original length L naught at initial temperature T naught, right? When its temperature is increased from T naught to T degree centigrade, yeah, if you can say that, let's suppose, for example, if I just label it as T1, and if now when you heat or when you supply the heat energy, then its temperature is increased to T2, such that delta T will be the change in temperature, and it will be T2 minus T1. This is the temperature. The new length of the object, or the final length of the object L, is to be found as like this. This is the apparent, this is the increase in the length of an object due to heating. Now, experiment shows that experiments experiments show that experiments show that the increase in the length of an object depends the first factor. It depends on the original length of an object. Original length of an object, right? That is the increase. This is the change in length increase. The change in length delta L is directly proportional to the original length of the object, right? It is directly proportional to what? To the original length of an object. This is one. Look, if you have two rods which have the same nature, for example, let's say that if you have like the two copper wires, for example, if you have one this copper wire, right? And if you have one this copper wire like this, if these two copper wires are of the same diameter, their diameter is the same, as you see, look, it has diameter D and it has also diameter D, right? Uh, oh my God, that is, that one has like this one, look, they have what? They have the same diameter. The diameter of both the wire is the same, right? But their length is different. So when you increase their temperature, for example, if both are at room temperature and if you increase their temperature by 5 degrees centigrade, then the wire with length L will expand more than the wire with length L dash. So the change in length delta L will be greater than the change in length delta L dash. So this shows that the increase in the length, the change in the length depends on the length of an object, the original length of the object. The second one is that it depends on the change of temperature, right? The rise in temperature. For example, this is the, in the same way, for example, if I have two wires, the look, for example, the steel or the copper wire, when I have this, as you see, another of the same length like this, okay? If they have the same length, you see, the lengths are the same, their diameters is the same, diameter D. Here the diameter D, here the diameter D, and here the diameter D. So you see they have the same diameters, they have the same length L and L. But if they initially, they share the same temperature T1, but if you rise its temperature to T2 and here to T2 dash, such that T2 dash is greater than T2, then this will expands more than the same wire of the same dimensions, right? So this shows that increase in, that is that the increase or the change in length is directly proportional to the change in temperature also. Mathematically, if we combine these two, then what will happen, that this delta L, which is directly proportional to L naught into delta T, right? And there is a third factor also that is coming here. And this delta L is equal to alpha L naught delta T, where this alpha is called the coefficient of linear thermal expansion. It is called what? The coefficient of linear thermal expansion, right? And this coefficient of linear thermal expansion, it can be written as, look, this alpha, it can be written as delta L into by L naught into delta T. Now, this purely depends on the nature, purely depends on what? Depends on the nature of the substance, on the nature of the substance. It does not depend either on change in length, L naught or delta T, right? It purely depends on the nature of the substance. Its SI unit is, if you see the length and the length unit cancel, it is per Kelvin. And how we can define this? We can define this as that it is in fact the frictional increase, the frictional increase in the length of an object, in the length of an object due to, in the length of an object per unit rise in temperature, per unit rise in, per unit rise in temperature, per unit rise what? Per unit rise in temperature. So that is known as the coefficient of linear thermal expansion. So it is different for different for different substances, right? And can only be calculated from the experiment. So keeping this thing into our mind, we can just rearrange our equation number first. Like for example, delta L, as I told you, that it is the change in length. So final length minus the initial length, you know, alpha, and if this is L naught, sorry, the initial length we have supposed as L naught, original length, L naught into delta T, or what we can write that the final length of an object could be like this, L naught delta T. Now, what does this mean? That the increase to the final length of the object will be 1 plus alpha delta T. So if you know the original length of an object and its coefficient of linear thermal expansion and the change in temperature, then you can easily find the final length of an object, right? So this equation is for the final length. For the change in length, you have only this equation, right? So this is second. And for finding the coefficient of linear thermal expansion, you have this equation. Now, I have devised in an experiment for you. If you just see, look at this sphere, the metal ball or metallic sphere, and then there is a ring. The metallic sphere is attached to the chain here you see and can be suspended freely. Now, when you allow it to pass through the ring, it can easily slips into the ring. When you allow it free, it will fall into the ring without any difficulty. Now you heat it, raise its temperature. For example, the initial, this is at some room temperature, okay? So now when you raise the temperature by heating the metal sphere, then with care, now insert this metal sphere in the ring again. What you will see that it will be now difficult for the sphere to pass through the ring. What is the result? The result indicates that once when you increase the temperature of an object, the size, it affects the size of an object. The size of the metal ball increases. Metal ball increases and now it cannot pass through the ring until it is cooled again. So it means that the increase in the volume is not just, the increase in the length is not just related to the increase in the volume, but it is also related to what? It is also related to the volume of an object also. So here you see, look, that if you apply this to the volume, as you have seen in the case of the sphere also, so in the same manner, this happens to the other parameters of the substance also. And this is what we now want to study or explain, the volumetric thermal expansion. Now, what is the volumetric thermal expansion? Volumetric thermal expansion. The volumetric thermal expansion, it is in no way different than the linear thermal expansion, in the linear thermal expansion, just in the way that it is the apparent increase in the volume of an object due to heating. Why? Because if you see, look here, when you heat a substance, then its all dimensions are affected. For example, if it is the original volume of an object, as you see, V naught. Now, after heating or increasing its temperature from T1 to T2, then definitely there is increase in the size of an object, as you see. Look, and the new volume which you'd see would like be this one. So here you see that the volume is increased and the rest of the equation is the same. For example, experiment shows us that the change in volume is directly proportional to the original volume of an object, exactly in the same manner as the change in length was proportional to the original length in the linear thermal expansion. And second, this change in volume is directly proportional to the change in temperature also, delta T. This is second. It is exactly the same. And again here, the third factor here is that it depends on the nature of the substance also. So if I combine these two equations into a single equation, so this change in volume will be directly proportional to the original volume and the change in temperature, as you see here. Now, look, if I proceed further, then it will become beta V naught delta T. Now, definitely you see the difference here. There, the coefficient of linear thermal expansion was alpha, and here the coefficient of the volumetric thermal expansion is beta. And this beta will be equal to delta V by V naught into delta T. And it is measured in the same unit like the per Kelvin. That is in per Kelvin, right? Now let's see that how we can define this. It is defined as that it is the fractional increase, the fractional increase in the volume of an object, in the volume of an object per unit rise in its temperature, per unit rise in its temperature, right? Now, but the most important point is that which you must remember is this beta is always equal 3 times alpha. What does this mean? That the coefficient of volumetric thermal expansion is 3 times larger than the coefficient of linear thermal expansion, and it is easy to understand. Why? Because for the volume you have 3 dimensions, right? The length, the width, and the height, and every dimension is affected by increase in temperature. This is one of the reason that if you calculate beta, it is 3 times alpha. So if you know the linear coefficient of thermal expansion, you can easily find the volumetric coefficient of thermal expansion. And this alpha is also equals that 1 over 3 times 1 over 3 times beta. 1 over 3 times beta. Now, so that is the for the linear coefficient thermal expansion. Now we have the merits and the demerits are the applications, and the demerits of what? The demerits of the applications, and the advantages are the disadvantages of the coefficient of of the thermal expansion. So there are questions, certain questions. For example, you might have seen that gaps are left while laying two section of the railway track. So here you see that between the two Now I will explain you the applications of the thermal expansions, right? As well as this includes the merits and the demerits of the thermal expansion of solids also. For example, you might have noticed that a gap is left between the two section of the railway track here, as you see. Now the question is that why the gap is left between the two sections of the railway track? Because you know that on hot summer day, summer day, the things expands on heating. So during the hot summer day, when the railway track is heated and when there is no gap between the two segment of the railway track, then they might expands and create a large uh, pressure, because you know, look, what is the force for what is the pressure force per unit what area. So if the area is very small, as you see, then even a small force can reduce a very large pressure, which may bulges the train track. So you see the distortion in the train track. This distortion in the train track is caused by what? It is caused by the expansion of what? By the expansion of the uh, by the thermal expansion of the railway track. So for this reason, gap is left, right? This gap is called the compensation gap. So here you see the compensation gap right here. So this compensation gap is compensation gap. This is left to cover the effect, right? So similarly, while placing the guiders of the bridge, here you see that, look, in order to provide this compensation gap for the bridges, here you see that the one end of the guider of the bridge is placed on the rollers, here you see like that. So and the other end is what? The other end is fixed, and here the one end is placed on the rollers, and then there you see the gap. Here the magnified view of the gap, you can see this gap. Okay, so that this gap is left. So when the concrete guider, when it spends on a hot summer day, so it may find place for its expansion and wouldn't exert tremendous pressure on the poles of the bridge, and in this way it will be kept safe, right? And a chance of danger will be minimize. Clear? So one is this thing, and the second important point here is the bimetallic strip. This bimetallic strip, it consists of what? It consists of two metal strips of the same length and size, but having different thermal coefficient of expansion. One has low thermal coefficient of expansion, and the other is having high coefficient of thermal expansion. So when it is heated, then after heating, because of this different coefficient of thermal expansion, the bimetallic strips bends. So the bending or the curve or the bending of the bimetallic strip is implied in various temperature controlling device, or even can be used as a switch. So now look, as you see here, that when this part of the uh, bimetallic strip, when this end is heated, that it bends, right? It bends in a way that the high expansion coefficient on the sides of the higher coefficient expansion material. This bending is then used in various applications. For example, how to make or break the circuit. For example, in controlling the temperature of the electric heater, right? You can see this in your book also. So this can be used as a thermostat. Similarly, using rivet in steels, as you look rather here, for example, look how this the application of this. Look, for example, if you have here the heater player, let me make a heater for. Here is a heater like this, as you see. Now, for example, this heater is connected one end with the positive terminal of the battery. This is the positive terminal of the battery, and this the positive, and one end with the negative terminal of the battery, right? And here, let me make the connection, as you see. Now look what happens, that in the normal condition, this makes a contact with the circuit, right? It is straightened. Look, that is when the temperature, when the heater is switched on, and when the temperature reaches a desirable value, and you know that it will expand on heating and contract on cooling. So it will, that is when its temperature rises, then this bimetallic strip will bend in a way that material with high coefficient of thermal expansion remain on the outside. It will bends in that direction, and what will happen, it will bends in a way like this, and the circuit will what break, and now the path of the current is incomplete, and the heater will switch off. Once that is the room temperature is again become lower, then with the passage of time, the bimetallic strip will straighten itself because of a decrease in temperature, and at one point it will make a connection again, right? And the heater will switch on automatically. And look, when the temperature reaches their desirable value, at that point, the bimetallic strip will bend itself so much that it will break the contact with the connecting points, right? The circuit, that is the current, the passage of the current will drop in the circuit, right? And the circuit will then act as an open circuit, and no current will flow, and the heater will automatically switch off. So these are the applications of what? The applications of the bimetallic strip. So the thermal, this is all about what? All about the thermal expansion of the solid. The thermal expansion of the solid, beside this, it is also used to produce a tight grip. For example, look how the wheel is fitted to its axle. For example, if this is axle, like this one, as you see, and look, if this is the wheel, so when the wheel is fitted to the axle, Normally the hole of the wheelhead made slightly smaller, then the diameter of the hole is slightly smaller, and this is D1 and this is D2. So D1 is slightly smaller than D2. Then the wheel rim, it is heated. When it is heated, the hole expand, as I did it to you right in the beginning. When it expands, then it can easily fit into what? It can easily fit into the axle, right? It is then cool. When it is then cool, it contract and give a tight grip to the axle, right? So this is how it can be used to make things fixed or stay together strongly. So these are all the applications of the bimetallic strip. Similarly, when you want to lose the metal cape of the bottle, then you and if it is very hard, then you place it in a hot water or you spill a hot water over it, and it expands, and when it expands it leaves capes and can easily be opened. So this is why to open the tight cape bottle we keep them usually in a hot water, right? So this is all the application of the thermal expansion of solids.